The most powerful thing about a balanced chemical equation is that it tells us about relationships between all of the different chemical species that are part of that reaction. So a balanced chemical equation lets us answer questions like, how much of something do I need to react, or how much product will I make from a given reaction? So if we look at a chemical equation like methane plus oxygen gives us carbon dioxide and water, we actually have a lot of relationships in this chemical equation. And if we think about it, what is this telling us? This chemical equation is telling us that one methane will react with two oxygens. Okay, so that tells me a relationship between reactants. It also tells me that one methane will produce one carbon dioxide. Looks like a relationship between reactant and product. Or two oxygens will react to form two water molecules in this chemical equation. Again, reactant and product. Or again, for every two carbon dioxides I form, or for every one carbon dioxide I form, I'll form two water molecules. So we can express these relationships in words, but we can also express them as ratios, as fractions. So there are two O2 molecules for every one methane molecule. There's one CO2 for every methane. So we can pick any two of these and form a ratio, and that ratio can be flipped if it needs to be flipped. Ultimately, all of these ratios are what we refer to as stoichiometry. So people often stumble over that word. Say it confidently and say it fast. Stoichiometry. And that is really where chemical reactions start to show their power. When we think about stoichiometry, when we think about those ratios, we can really think about those ratios sort of as conversion factors between any two species in a chemical equation. So just like with any conversion factor, let's treat it that way, and more importantly, let's use dimensional analysis. Let's use our units to make sure that we're flipping it the correct way for the problem we're looking at. So here we've got our chemical equation again. How many CO2 molecules are produced from 68 oxygen molecules using this equation? Well, here are all of our ratios. Start with what we know. I know that I've got 68 oxygen molecules, so 68 oxygen molecules. And then what am I looking for? I'm looking for the relationship between oxygen and carbon dioxide. So for every two oxygens, I get one carbon dioxide in this chemical equation. If I want to cancel my oxygens and get carbon dioxide, I'm going to put it as one carbon dioxide over two oxygens. And if I do that, I will cancel those units out, and I'll be left with number of carbon dioxide molecules. So 68 divided by 2 is 34 carbon dioxide molecules. Now, just as a quick little side note here, because we're working with whole numbers, oftentimes this math seems like this is a lot of work to do divide by 2. And in some ways it is, but it's really important to think about this process and really think about it this way, so that when we move on to the next step in some of these types of calculations, we've got this established and we know how to use that stoichiometry, how to use that ratio to go through a conversion like this. So even though at this point it might seem like this is a ponderous way of doing this conversion and answering this question, go ahead and get used to setting it up this way, because it'll help you a lot moving forward. So what do we use stoichiometry for? Here we've got one that's fairly straightforward. How much carbon dioxide do we form from a given amount of reactant? So how much product from a given amount of reactant? We can also use stoichiometry for what I call reaction planning. So if I've got two reactants, how much of reactant A do I need to react with reactant B? So here we go. How many O2 molecules are needed to react with 47 methane molecules? So if I've got 47 methane molecules, how many oxygen molecules do I need to perform this reaction? Well, again, let's set it up as sort of a conversion factor using that stoichiometric ratio of 2 oxygens for 1 methane. And again, set it up so that our units cancel appropriately. And we see that for 48 methane molecules, I need 94 oxygen molecules. So reaction planning, one way that stoichiometry gets used a lot in the real world especially. We can also look at something called a limiting reactant problem. So let's think about this. If I've got 2 reactants and I've got specific amounts of both of those reactants, what are the chances that I'm going to just accidentally scoop out the correct amount of both so that they perfectly react with each other and nothing's left over? Probably not, right? If you're making a cheese sandwich and you've got 20 slices of bread and only 2 slices of cheese, you're going to be limited by the amount of sandwiches you can make by the cheese. It's going to run out before you run out of bread, unless you have a really weird sandwich. But these are the thing that runs out first limits the amount of product that can be formed. So these are limiting reactant problems. There are a few different ways to approach these, but let's just look at one. If I've got 84 oxygen molecules and I react those with 52 methane molecules, so I've got a specific number of both reactants, which runs out first and how many of the excess reactant are left? So limiting reactant is what runs out. Excess reactant is what's left over at the end. So again, same chemical equation. Let's take a look at our 52 methane molecules. How many oxygens do I need to react with 52 methane molecules? I can set up that ratio, and I see that for 52 methane molecules, I would need 104 oxygen molecules. But I don't have 104 oxygen molecules, I've only got 84. So that tells me that the oxygen in this case is my limiting reactant. It's going to limit the amount of product I can form. Let's look at the other direction. 84 oxygen molecules react with how many? 1/2, 42 methane molecules. 42 methane molecules are needed to use up all of the oxygen. I have 52 methane molecules, so I have 10 more methane molecules than I need. I'll have 10 leftover methane molecules when all of the oxygen gets used up. So again, cancel those out appropriately so that you're setting up your units the right way. And that's really the heart of stoichiometry. So a couple of things. First, the most important part of stoichiometry is having a balanced chemical equation. And remember, the most important part of a balanced chemical equation is a balanced chemical formula. So we kind of go all the way back to balanced chemical formulas, which we then make into balanced chemical equations, which we can then use in stoichiometry problems. The ratios that we see in that correctly balanced chemical equation describe the relationship between products and reactants, reactants and reactants, reactants and products, products and products, any combination of those. And really get in the habit right now of setting them up like any other conversion factor problem. Again, for a lot of the ones that we're doing right now, the examples I went through, they seem a little trivial as far as those ratios, but the reason they seem trivial is because we're using lowest whole number coefficient balanced chemical equations As things move on, as we get into more complex systems, it'll be a huge benefit for you to be setting these up, as I just showed you, sort of as a conversion factor moving forward. It's another practice, right? Lots and lots of practice, building up on all of those steps that get us to a stoichiometry problem. So look over some problems and good luck on those. See you next time.